Hello, physics students, and in this video we're going to look at the conservation of energy. We're going to look at mechanical energy, the conservation of mechanical energy, and we're going to look at mechanical energy and how friction affects that. So you all are familiar with this idea of the conservation, the law of conservation of energy. Energy cannot be created or destroyed. That similar concept we see in regarding mass. Matter cannot be created or destroyed, the law of conservation of matter. But energy is definitely conserved. It means it remains constant when we look at the overall total. It doesn't mean that energy never changes. It can be converted from one form to another or transferred one place to another. Those are just some examples of energy transformations that can happen. You know that chemical energy can be converted into kinetic energy, as in this example. I'm not sure that, well, I guess if he's riding a bicycle, kind of looks like a motorcycle. But that chemical energy can be converted into kinetic energy or thermal energy that we use to keep ourselves warm. The radiant energy from the sun is converted into chemical energy via photosynthesis. Chemical energy here is converted into kinetic energy and thermal energy as well. You know that because your engine gets very warm. Electrical energy is converted into thermal energy. Those are just some examples. So when people talk about conserving our resources, sometimes you might get the wrong idea. Let's save energy. Well, remember, the total energy always remains constant, but the usefulness of that energy can change. So, for example, you have chemical potential energy in the gasoline that you put in your car. And when you are sitting there driving your car, you use that chemical potential energy and it's converted into kinetic energy and it's converted into thermal energy. That thermal energy warms the air around your car. And at that point, that chemical potential energy is no longer available. That energy has been converted into a different form of energy. And the form of energy that it's been converted into, the thermal energy, is no longer useful. You can't go around and collect that, put it back in your gas tank, and reuse it. It is not useful in that form anymore. So remember, the total energy always remains constant. The usefulness of that energy can change, however. So when we talk about energy, we usually classify it into two large groups, mechanical energy and non-mechanical energy. Don't be confused by the title of this. Mechanical energy simply refers to kinetic and potential energy, whereas non-mechanical refers to other forms. Some examples of non-mechanical would be like thermal energy, internal energy, electrical energy, nuclear energy, and those are not considered mechanical. When we talk about mechanical energy, we're talking about kinetic energy and potential energy. The two forms of potential energy that we're going to look at more in depth are gravitational potential energy and elastic potential energy. So let's talk more specifically about mechanical energy. In the absence of friction, mechanical energy is conserved, and we can say that the mechanical energy is going to equal all of the kinetic energy and potential energy, the sum of all the potential energy as well. This includes the gravitational and the elastic potential energy. Again, it does not include nuclear, thermal, electrical, or chemical potential energy. It is not the total energy of the system altogether. Realize that if some of the mechanical energy is converted into thermal energy, then we're not talking about mechanical energy is still conserved, but if some of that energy leaves the system and we no longer have that closed system, if some of the mechanical energy is converted into, say, thermal energy, and therefore then that will not work. We'll talk about that in a little bit. But if we look at a system and we're disregarding the friction in that system, then we can think about the sum of the kinetic and the potential energies equaling that total mechanical energy. A falling object, for example, if we have an apple here on this tree, at this point, this apple has its greatest potential energy. When this apple falls to the ground, at this point on the ground, that apple has no more potential energy relative to the ground, but just before it hits, it would have its greatest amount of kinetic energy. In between, as the apple falls, that potential energy is being converted into kinetic energy, and at different stages along its travel, along its path, it will have different amounts of potential energy and kinetic energy until it reaches this point at the bottom. If we look at projectile motion, we can think of this point right here. The kinetic energy at this point would be the lowest, would be 0. There is no motion right here, right at the top of its trajectory. There's no kinetic energy. However, just before the ball hits the ground, it would have its greatest amount of kinetic energy. And at that point, its potential energy would be 0 when it is just about to hit the ground there. At this point up here, it would have the highest amount of potential energy, and then it would be varying degrees all the way in between. As the potential energy is converted into kinetic energy, has less and less and less kinetic energy, less and less and less potential energy, and more and more kinetic energy as it travels here. Same with the swing. We have here and here, those positions would be the highest amount of potential energy, and right at the very top here, you'd have no kinetic energy when the swing is at that moment of stopping and changing directions. Here is the point at which the kinetic energy would be the greatest and the potential energy would be lowest. So mechanical energy is conserved. The amount that we start with of total mechanical energy will be the amount that we end with in a closed system. So that means in the absence of friction, because friction generates thermal energy, and that's energy that is outside of the parameters of our system, so that's different. But in our closed system, mechanical energy is conserved when there's no friction, means the initial mechanical energy is equal to the final mechanical energy. We can substitute values in for this. We know that the initial mechanical energy is going to be equal to the initial kinetic energy plus all of the initial potential energy. And we know that the final mechanical energy is going to be equal to the final kinetic energy plus all of the final potential energy. We can substitute those values in. We know that kinetic energy is equal to 1/2 mv squared. So 1/2 m initial velocity squared plus my initial potential energy is just mgh, h being the initial height for that involved in that initial potential energy. We can substitute then the value for 1/2 mv squared right here, 1/2 mv squared, the final velocity in this case squared, and the potential energy, the final potential energy is just mgh, h being the final height. So let's try a little practice problem here. Say we have some penguins, and they are, we have a penguin here starting at rest, and he slides down a frictionless slope of ice. How about this penguin? He was first down. Starts at the top, slides down to the bottom of a frictionless slope. The slope has an initial height of 5 meters. Penguin has a mass of 10 kilograms. And what is the penguin's speed at the bottom of the slope of ice? So first, let's write down all of the variables that we do know. We know that the initial height is 5.00 meters. The final height is 0.00 meters. We're going to say this is relative to the bottom of the slope. The mass, 10.0 kilograms, and the initial velocity is 0.00 meters per second. And we are supposed to find the final velocity. So let's start this problem by thinking about conservation of mechanical energy, because indeed we actually have a frictionless slope. So we can say that the mechanical energy initial is going to be equal to the mechanical energy final, and that means we know that the sum of the mechanical energy, it's going to be the kinetic energy initial plus the potential energy initial. It's going to equal the kinetic energy final plus the potential energy final. We can substitute in our equations for that. We know that for the initial kinetic energy, we have 1/2 mv squared for the initial velocity. Our potential energy initial is just mgh initial. It's going to equal our kinetic energy final velocity, plus the potential energy final, which is mgh final. Now we can plug values in for this. We know that initial velocity right here is 0. Therefore, this entire term will be 0. We can plug in values for the mass times gravity times the initial height. So I know that my mass is 10 grams, my value for g is 9.81, and the initial height was 5.00 meters. Now I can plug in values for my final kinetic energy and final potential energy. My final kinetic energy is going to be 1/2 times the mass, 10.0 kilograms, times the final velocity squared, which I don't know. That's the term I want to find out. My final potential energy, realize my final height is 0. So the term here will end up being 0 as well. Now, if we do a little bit of, you can plug values in or not, but this makes it really easy. I know my 0 terms are just canceling out here. I am then left with this term of all multiplication and division and this term of all multiplication and division. I can actually cancel some things out. I can cancel out the mass. It cancels out on both sides. So I'm left with my final velocity squared being 98.1 meters squared per second squared. If I take the square root of both sides, I end up with my final velocity of 9.90 meters per second. And that is how fast that little penguin is at the bottom of his frictionless slope. So in the presence of kinetic friction, mechanical energy is no longer conserved when we have friction. And that's because that non-mechanical energy is not negligible. It is not considered to be negligible. And examples of that would be this example. You're sanding some wood with a piece of sandpaper, and that kinetic friction generates, you know this, thermal energy, right? It gets warm. That means that the non-mechanical energy, that thermal energy, is no longer negligible, and therefore we cannot consider this to be a closed system where the mechanical energy is conserved. It is not conserved in that case. You know also when you swing on a swing, you continue to have to put energy into your swing because you don't just swing indefinitely and go on and on forever and continue to rise to that same high level of swinging that you do each time. You have to put energy. You have to pump your legs and your back and put energy into the system. That is because friction is involved. There is air resistance. There is also friction at the point of contact between the swing and the bar up here where it connects. And that produces a little bit of thermal energy, which again is not negligible. Therefore, you have to continue to pump energy into that system because the mechanical energy is not conserved because of friction. Here is another example. When you drop a ball, that ball will bounce, but it does not achieve the same height that it was initially, from which it was initially dropped. It's a little bit lower. That means from here, this potential energy is being converted into kinetic energy until the point that it hits the ground. At the point that that ball hits the ground, some of that kinetic energy is converted into thermal energy. And so when the ball rises again, it will not achieve the same height because some of that energy, that mechanical energy, was lost to something other than mechanical energy, some thermal energy. And you can see this as it goes on, a little bit of mechanical energy each time it hits the floor due to friction is lost to non-mechanical energy or thermal energy. An advanced idea. Try solving the problem in the video by
writing the equation down and then writing the answer in terms of variables only. Then in the very last substitute, you can in the very last step, substitute the given values into the equation and solve. Just a different way of thinking about how to set up a problem, and you can certainly rearrange the entire problem in terms of variables only, and then substitute values in for your variables at the very end. I look forward to seeing what you have to come up with. If you have other advanced ideas, please feel free to do those as well, and we'll see you in class.